Hello everyone, welcome to our Lab 2 video. In our previous video, we went over histograms, bar charts. Remember that bar charts were used only for categorical data. Also, they work when you have discrete variables but with few possible outcomes. In the case of the histograms, we can use them for continuous variables, even discrete variables, numerical, they will work. Now, histograms, they were very convenient many years ago when we didn't have computers because they were easy to draw by hand. It's possible. Now, since we already have computers, another alternative for continuous variable is to use density plots. So remember the probability density function PDFs. This is how they look. And they are useful when you want to analyze the shape of your data. So typically the first thing that you will see in with your density plots, it's whether your data is symmetrical or not, like in this plot in the middle, or if it's skewed to the right, in case if it's positive it's skew, or if it's negative skew. Now, on top of that, this is important because we can identify some probability distributions. I'm pretty sure that most of you have seen the normal distribution. This is the most popular by far of all the continuous distributions. But we have other probability distributions. For example, the uniform probability distribution is where for every interval that you take here, if you take like an interval of the same size, the probability is going to be the same because it's uniformly distributed. Now, another interesting probability distributions, one of them is the exponential distribution, and it's heavily used when we are modeling times. For example, the waiting time, if we are analyzing a supermarket, or maybe if you're calling to a call center, so there is a waiting time, like the time it takes for you to reach an agent to get some information. So you can model that time as an exponential time, as an exponential distribution. All right, so the idea of density of these density plots is to see the shape of our data. Okay, so let's use the penguins dataset. This is a popular dataset. There are some datasets that typically are used when you are working in data science. For example, the IRIS dataset, Titanic dataset, cars, and penguins is one of them. Okay, so let's bring our data. It's in Seaborn. So let's load the dataset. The name is penguins. Let me make sure that the libraries are available. Yeah. So let's see what information is available in this dataset. Okay, so we have a variable, categorical variable species. There are 3 species. The island, and we have some information about the measurements of each of the penguins. We have the bill length, the bill depth, flipper length, body mass, and the gender. Okay, so in this particular case, I'm going to focus on a continuous variable, the flipper length. I can use a histogram here, but since we are talking about density plots, I'm going to use a density plot. So from Seaborn, let's use the density plot. And we're going to talk about the flipper length. Okay, So we get the plot, the density plot, and here we can check whether it has like a single mode, like unimodal probability distribution, or if you have two or more modes. Remember that the mode is like the most popular value. In this case, we see that there are two peaks, right? So typically, this suggests that there are multiple populations in your data. But it's not clear here. Of course, there is there are two peaks, but it's not clear where are the populations. So if we check our data, now it's reasonable to see that these variable species may have an influence, right? Because maybe the species are really different, and then the length of different body parts might change. So let's add that variable to our analysis. You're going to use color with hue. Let's add the species. And now we're getting something more interesting. You can see like three distributions, one per species, but we see that the mean value, the median, they are shifted. So let me add some color here. I'm going to fill each density plot. Right, that's it. So for instance, we see that the Gen 2, the flipper length, which is in the x-axis, it's bigger compared to the other penguins, right? So in addition, we can say that, for example, the Adelie penguin species, maybe they have the flipper length is smaller, right? Because we see that the mean value is around 190, right? Now in the case of the chin strap, it's between 190 and 200, and in the case of Gen 2, we see that it's like around 215, right, and 220, the mean value and the median too, most likely. So we see a difference. These distributions are shifted, so they suggest that they are different. Now another alternative here is we can add a box plot to see the differences. So in the x variable, we're going to have the species. With an S, species. And in the y variable, I'll use our variable of interest, the flipper length. I'm just going to copy and paste it from here. Right here I'm using Plotly Express. So we have we get the three species and the flipper lengths, and we see that the boxes, they are not at the same level, right? You see that in 2, the median value, which is this line inside the rectangle, it's way above the other boxes, suggesting that the Gen 2, that specific species, the flipper length is higher, right? It's longer. Therefore, my first hypothesis will be that the flipper length depends on the species, different. Most likely, if we use a test, like doing hypothesis testing, we will find that they indeed are different. So you can do here an ANOVA to check whether these three mean values are the same or if they are different. I highly encourage you to do the ANOVA test, or even Kruskal-Wallis test, which is a non-parametric test to compare the mean values. Because this is just exploratory analysis, what we're doing right now. But if you want to start making some conclusions, like this one is bigger, this one is smaller, you need, or my advice to use some inferential statistics, so hypothesis testing. So in the ANOVA analysis, you need the null hypothesis and the alternative hypothesis. The null hypothesis will be that the mean values are the same for the three populations, and the alternative is that at least one of them is different. You need to perform the test, you will get a p-value, and the p-value, if it's smaller than the alpha, which typically it's 0.05, because if you use a confidence level of 95%, then in that case, if it's smaller, the p-value, you will claim that you reject the null hypothesis, therefore the means are different. But if the p-value is greater than the alpha value, then we do not reject the null hypothesis. In this case, if you do the test, which I encourage you to do it, you can use AI, guys, to use the functions, as long as you know how you know what is the hypothesis and also the interpretation of the p-value, you will be fine. All right. So now let's go over a different example. This one is from a data set. The name is tips. So the data set has different variables, the total bill. We also have the sex, we have the smoker, the day of the week, time, if it's in the, like morning or dinner or lunch, and the size of the party, number of people. So let's bring that data. There you go. So this is our data set. It has 244 observations. Now we want to see whether there is a relationship between the tip percentage and one of these variables, sex, day, or time. So let's separate analysis here. So the first thing I will do is to add a new column. I'm going to create a new variable. So in tips, the new variable will be tip percentage. Just going to add a new p, which is going to be the tip divided over the total bill. So that will give us a percentage. Here I'm missing something. There you go. Now it's working. So we have computed an additional column here, which is the percentage. For example, for the first observation, the tip percentage was 5.9%. In the US, that's a personal preference, but I will say that it's a small value. Let's see the average value. So let's describe our data set. Then the tip percentage, the average value, it's 16%. And the median is 0.15 or 15%, 15.4%. All right, now let's analyze individually the tip percentage with the categorical variables, with sex, day, and time. Okay, so let's do a density plot. The tip percentage and sex. So initially, just by looking at the density plots, I don't see a difference. They are aligned. So when I will say that there is a difference, if one of the density plots is shifted a little bit to the right or to the left, and you see that they are not aligned, they are not centered around the same values, then you can claim that there might be some differences. However, remember, this is just exploratory analysis. You need to perform a statistical test to confirm whether they are the same or not. So in the case of the gender, initially I would say that there are no differences in terms of the mean value. However, again, it's important to do a formal test of that. Okay, I'm going to change it now for time. And then for day. So this is lunch, dinner, again similar. Clearly, there is no a clear difference in the mean value. And with day, It's slightly shifted in some cases, but I don't know if that difference is big enough to claim that they are different. Again, a statistical test can help you to arrive to a conclusion. So here, since we have multiple density plots, I think it's better to use a box plot where you can see like the differences, right? So let's check real quick a box plot. Let's do it with day. Okay. Then the median maybe is a little bit higher for Sunday. You see the line, but again, it doesn't look that is a statistical significant difference. And this by looking just at the plot. Now there are some atypical values here, outliers. For instance, on Sunday there are two observations. One, it's like around 40%. So yeah, that's high tip. And there is one that is above 70%. So typically when you see the outliers in your data, you need to check, to see whether that makes sense or not. So there are two possible explanations here. Maybe it's an error, a mistake in your data. Also, and that happens, there might be an error when the person was, like writing down the tip. Maybe that there is a mistake over there, right? Or maybe someone was just happy, with the service. I don't know, but 70% looks high. Now it depends of the total bill, right? Because maybe 70%, if the bill was not that big, that's fine. But yeah, this is where you need to start analyzing your context to find what is the explanation for those outliers. Because if there's an error in your data, it's better to remove those outliers. But that will depend on the context, of course. Okay, so as you see, we're using here different plots to start to understand our data. Let me go over the scatter plots, which are really useful when we're comparing two variables, two numerical variables. So typically we use scatter plots to identify whether the variables are correlated or not. So there are relationships, and that's really important, especially when you're doing like regression models, when we want to predict a numerical variable y using some predictors. It is important that there is a correlation among our variables. So we use scatter plots to visualize that relationship. Same thing to identify outliers when you want to see clusters, like points that are close to each other, observations that are similar. So yes, we can use scatter plots. And also if we want to see trends to see whether it's increasing, decreasing, if it's a linear relationship or non-linear. All right. So for this, for the scatter plots, let's use the Gapminder dataset, which we used in our previous lab. I'm gonna add that library here. There are two options. You can upload the file as we did in the previous video, or I found that there is a library with the same name. The thing is that it's not available just to import it, we need to install it first. So pip install. This is when we're using a library that is not available in the Colab environment. So we need to install it. So this is normal. So let's install Gapminder. And then from Gapminder, we're going to import the dataset Gapminder. Typically, when you add a pip install, once I run it, I prefer to add like the number sign here, a hash, the hash symbol, because this is going to make this as a comment. Now why? Because okay, once I have installed Gapminder in my session right now, then I don't want to install Gapminder like every single time I run this in the same session. So I prefer to add the comment. In this case, the library Gapminder is small, it won't take a lot of time. But sometimes you're using, like libraries that are heavy, that will take it will take longer to install them. So once you install them in your session, it's better to just make the comment so you avoid, like all the downloading and installing again when it's not needed. Okay, so Gamma Network is available. Let's bring our data. I'm gonna create a condition just to get the latest year as we did the other day. So only 2007, that's the most recent year in this data set. It's going to be df, the data frame again. So we're going to filter using year equal 27, 2007. Okay, now we have our data set with observations only of the most recent year in here. All right, now in this particular case, the question is suggesting, okay, we want to analyze the life expectancy and the GDP, the gross domestic product per capita. That's per capita. So that's the GDP divided by the population of the country. So it gives an idea of the life quality, the income of the population. It gives you an idea. It's not an exact value. All right, so let's see if the GDP per capita has an impact in the life expectancy, which makes sense, right? I mean, it is expected that if in a country the GDP per capita it's high, then we expect to see a higher life expectancy. So let's do a scatter plot. There you go. So using data 2007, X will be the GDP and Y the life expectancy. And yes, there is a relation. It's not linear, but there is a relationship, right? The notion is that as the GDP increases, the life expectancy increases. So we see some interesting observations here. For example, I would be interested in this area here, like in this area on top of the like above 70 and below 10,000, because it suggests that these countries, even though the GDP is not that big, the life expectancy is high, so they are efficient. They offer like a good life quality to the inhabitants of that country. On the other side, there are some countries with a high GDP but low life expectancy. That's pretty bad. That's not expected. That's not good. The problem with this plot is like it's static. You cannot like see the labels here like for each point. So an alternative here is to create a Plotly Express scatter plot. This is a basic one. Now I can hover the data and I can see the exact value. I don't see the country. So let's start adding more information here. I can add the color to show the continent. So for example, you see here Africa. I'm pretty bad with the colors. I do apologize for that. But for me, I believe this is like green. I'm not sure. I do apologize for that. I cannot differentiate between some colors. But yeah, I mean, you see that there is a continent here, like most of the continent is in this area, and that's Africa. You can see in the rest of the plots. Another thing that we can add more parameters here. One is the hover name. The hover name means like when you hover over the observations, you can see a variable. In this case, I want to see a country. So hover name country. If I update my plot, now when I hover, you can see the observations. So remember this observation that I mentioned that they are not good, like they have like high GDP but low life expectancy. So we have South Africa, Equatorial Guinea, Botswana, Gabon. So that's not good. On the contrary, for example, there is Vietnam here with a relative small GDP, but a decent life expectancy. So this is important because you can get some context. If then we can dig deeper and try to understand where are the policies and why this is true, why it's happening this. We can keep adding more features to our plot here, more variables. So one option is, for example, I can add the population. So that each observation, the dot is gonna take the size of the population. So for example, I'm pretty sure you can spot China and India easily here, right? So we have China here, we have India here. High population, then you see that the dot, it's bigger. And let me add one more. Since in the original data set, remember that we have many like different years. We have the same information for different years. So I'm going to use the original data set. So instead of DF 2007, I'm going to use the complete data set, and I'm going to use the information of the year to animate the plot. So I'm going to add animation here, but I need a time frame. Animation frame per year. And that's it. So animation frame per year means that like the plot is gonna update with the year. So once the plot is ready, now you notice that there is like a play here, play and stop. So if I hit play, then I'll see animation, right? So we see the year, how the year changes, and we see the evolution of our variables. So here what you see is that it's increasing, right? Which makes sense, right? This is like a 50-year data set. Even though we don't have like every single year, it shows the trend that most of the countries are improving their life expectancy, right? I mean that's I guess that makes sense because our healthcare system are getting better. You know, there are some innovations, vaccines, and things like that that in general they will tend to improve life quality, life expectancy. All right, so I'm gonna stop the video for today. I hope you enjoyed our session.